Hey class. So chapter 5 is diving deeper into a certain kind of matrix and certain kind of relationships, and that relationship is orthogonality. If you remember from early on in the class, orthogonal means perpendicular. The reason we don't just say perpendicular and we have another word is perpendicular makes sense when you're talking about lines and planes. Orthogonal generalizes the idea to other objects. You can have functions that are orthogonal to other functions in a way that doesn't make sense. It's like there's no 90-degree thing happening. So mathematicians saw that there was a need for another word to be more general than just perpendicular, so they call it orthogonal. So start off with the definition. Well, even before we do the definition, we're going to build up to something called an orthogonal matrix, and they have really, really nice properties. Some of the things that we have found hard before, like solving a system of equations and finding inverses, all of a sudden they are super, super easy if you have orthogonal matrices. And the transformations keep lots of things. They don't skew things. Distances stay the same and angles stay the same if you're doing a transformation with an orthogonal matrix. So these work out to be really, really nice in practice. So if you can work with one or change what you're working into one, then it makes a lot of things very easy and straightforward. So an orthogonal set of vectors is a set where each one is orthogonal or perpendicular to the others. And the way we know how to test for that is with dot products. So we can test to see if all three of if this is an orthogonal set with these three by just doing a dot product with each pair. And you can go ahead and do that and see that they're going to be at 0 in every case. So those three vectors will be an orthogonal set. If you have an orthogonal set of vectors, as long as one of them is not 0, then they are linearly independent. I mean, intuitively, you have two vectors are dependent if they're in the span of others, or if it could be pointing. If you just have two vectors, they're going to be independent if they're not pointing in the same direction or they're not lying on the same line. And so if they're orthogonal, they're pointing 90 degrees to each other, that can't be the case. And if it's orthogonal to everything in the set, then it's pointing in a different direction than all of the other ones in the set. So that kind of makes sense that they're linearly independent. And it forms a basis for the subspace it spans. So if they're all independent from each other, then it'll form a basis for our M, if you have M vectors. So you can scan through the proof there. An orthogonal basis. So here we're talking about up here we're just talking about an orthogonal set of vectors. Now, if you take a set of orthogonal vectors, they can form a basis. And so if all of the vectors for your basis are orthogonal, we call it an orthogonal basis. Here's two vectors. We can do the dot product to verify that these are orthogonal. So you get a 2, because the 1 times 2, you get 0, and you get a negative 2. When you do the products and you add those, you add 2 plus your negative 2, you get 0. We want to add another vector to this set, but we want to keep it an orthogonal basis. So we want to add not just anything that's linearly independent. We want to add a vector so that it is it's orthogonal to these two. So our task is to find V3 so that adding V3 maintains it being an orthogonal basis, or an orthogonal set, and it's a basis for our 3. So there's a couple different ways to do this, but the easiest way is to do dot products, and you create an arbitrary vector x, y, and z, or a, b, and c, you dot product with the first, and so you know that, and you want each of these to be 0, right? That's the key. So you dot it, and so you know x minus 2z has to equal 0. And you dot it with the x, y, and z with your other one, and then you know that 2x plus y plus z equals 0. And now you have a system of solutions to find a system of equations. You can find the solution, and we have a few different ways to do that, but you can row reduce, and you get this system. So we've got one free variable. Makes sense that we'd have a free variable because there could be lots of different vectors that we could put in there. If one is orthogonal to the others, we could scale it, and it would still be an orthogonal matrix, an orthogonal vector. So it makes sense we have a free variable because we should be able to scale something and still be okay. You do the solution, and you get that any vector times 2, a minus 5, and 1, it's at least a non-zero multiple of that, will work. So you can just take that one and add it in there. And you can check and make sure that pairwise each of these is orthogonal to the other one with dot products. So find an orthogonal basis for the subspace. So there's a couple different ways to do this one. The slick way is the way that previous professors already done it here. If you write this down, you can think about this as already being a system of equations that's in row reduced form. And so you could think of it as being 0, 0, 0, 0, 0, 0. You can think of it as an augmented matrix and you just have 1, 3, and a minus 1, and then we'd have 2 free variables. And so then you can rewrite the solution to any of those as he does over here. So a minus 3, 1, and 0, and 1, 0, 1. Both of these will be vectors in of in this plane, but they are not orthogonal necessarily. We can check and make sure. So are they orthogonal? A minus 3 times 1, we get a minus 3, and 0, and 0. So adding all that up, we still get a minus 3. So they're not orthogonal. So how are we going to do that? Well, we need to find a vector in W so that either if we take the dot product with one of these, it's going to be 0. So one way to think about what's happening is we have something like this going on, and we need to find, if we find something like that, we can get rid of that one. Or if we find something like that, we could get rid of that one. But we can keep one of those two for sure. So the easiest thing to do here is to think, oh, well, if I have, I can easily see what I'd need here. Well, actually, both of these are pretty easy. If I have 0 and then a number and then 0, if I dot product that, it's always going to be 0. So I could pick 0, 1, 0 to be basis. Oh, I better make sure it's in. I might have just lied because I better make sure that that falls in here too. Let's move on. So here we're going to pick x, y, and z has to equal x, y, and z dotted with 1, 0, 1. That's kind of the process I was talking about here, like picking one of these. And I said, oh, we should have 0 something 0. That should work. But the same problem that I bumped into, we're going to learn how to solve, right? Because I just said, oh, I should just be able to like pick 0, 1, 0. But I need to make sure that I'm still in the same plane. So if I dot this, we do get that x plus z has to equal 0. And we still have to be in the same plane. So we have 2 planes. We have more restrictions here. We can set up our system, go ahead and solve, and we get and we get anything along this line. So my 0, 1, 0 wouldn't work because it wouldn't be in that plane. But a -1, 2/3, 1, or any scale of that does work. So, and we notice we dropped the other one, that -3. Let's go back. That -3 is 1, 0. We replaced it with our new one because it's only a two-dimensional. It's just a plane. It's just a two-dimensional subspace. So we only need 2, and so we got rid of that other one. Okay. This. At first, when you see this, it looks really technical. This is amazing, okay? This is a phenomenal theorem. So if you have an orthogonal basis for a subspace, then, and you want to find how y, like what are the coordinates of y in this subspace, like to be clear, like if this was like a 3 by 3, what you're saying is, oh, I guess I could have. Let's do x, y, z equals 1, 2, 3. So I want to be able to write this vector with an orthogonal subspace. So these are not orthogonal. I'm just trying to write down something. These are orthogonal, but this is like too easy for us. But if this is a subspace that's orthogonal, if this matrix is orthogonal and we're trying to use the basis here, then usually we have to row reduce. Okay? Let me pick something else. Oh, I should have had a better example here. So usually we have to row reduce to find out the system, right? Whatever it is. Usually we have to row reduce to figure out what x, y, and z are. If these are orthogonal, if each of these is orthogonal to the other columns, then you don't have to row reduce. There's a formula to tell you exactly what x, y, and z are, and this is the formula. You may have it may look familiar to you. It looks like the projection formula. If we project the projection of u onto v is u dot v, v dot v, and we multiply that all times the vector v. So this part here is exactly the same as that. But this is actually multiplied by another vector. We really are just projecting this vector y that we care about. In my example, it's over here, this 1, 2, 3. We're just projecting it onto each of the basis vectors, and the coordinates just tell you how much you go in each of those basis vectors. Well, that's what the coordinates tell you anyway, but you can find that just from projection. And that's the slick thing. We can just do a projection, which we already know how to do, and that will tell us our coordinates. And that works if you are dealing with orthogonal matrices, an orthogonal set of matrices. So it makes solving systems of equations super, super easy because you already just have a simple formula, and it's not, it's intensively, like it's super efficient to do the calculations. So, and the proof here, it's also slick. So if you want to find out what C1 is, then you do the dot product of U1 on both sides. And because U1 is orthogonal to all of the other matrices, the dot products are going to be 0. So you just end up with C1 times U1 dot U1, and you can divide by that. It's just a number on both sides, and so you just end up with the what we have up there. You just end up with this the formula for each one, for each coefficient. So it is the projection. It's how much of the, yeah, never mind. Okay. And that works for any of the C's. So here we have a set of vectors. They form an orthogonal basis for R3. Find the coordinates of this. Well, usually, if you didn't know this was orthogonal, you didn't know the last theorem, what would you have to do? You'd do, okay, 3, 0, 3, minus 1, 0, 1, 0, 5, 0, and augment it with 2, 3, 5, and then start row reducing. Okay, and maybe this one still isn't that bad, but this saves us a bunch of time. Here, if I want to find the coordinate of v1, then you do the dot product, v1, y dot v1. So that's going to be a 6, 0, and a minus 15, which is a minus 9 right there. And v1 dot v1, which is 18. You get 9 times 9, 0, and 9 times, 3 times 3, which is 9, 0, and 3 times 3, which is 9, so 18, a minus 1/2. Boom. So I already know that that the solution here, if I think about it as x, y, and z, well, x1, x2, and x3, x1 is going to be a minus 1/2. Slick, huh? And then you can do the same things for v2 and v3. Find what x2 is, do the dot product of these two, divide it by the dot product of v2, boom, tells you what your coordinate is. Super slick. So a set of orthogonal vectors is called orthonormal if each vector is a unit vector. So these, if we go back, these aren't unit lengths. Okay, this has a length of 5, this has a length of like the square root of 2. Okay, these have different lengths. So now what we're doing is we're going to make these or keep these orthogonal, but we're going to divide by the length and make sure so the length is 1. So how can we make this an orthonormal set? You just divide by the length, and the length is the square root of the dot product, right? So v1 is the square root of v1 dot v1. Okay, so that's what they do down here, and you divide it out, and now we have an orthonormal set. And it just brings tears to my eyes about how nice orthonormal sets are. So if you make a matrix with an orthonormal set, you could try this, and let's multiply it u times u transpose here. So 1 over the square root of 2, minus 1 over the square root of 2, 0, 0, 0, a minus 1, and 1 over the square root of 2, 1 over the square root of 2, and 0. So this is u transpose. I already transposed it. So what do we get? I get 1 over the square root of 2 times 1 over the square root of 2, which is a half, and then I get another 1/2. Those will become positive and 0, so I get 1. And here I get 0, 0, 0. And here I get 1/2, a minus 1/2, and 0. And then here, first row, second column, I'm going to get 0. First row, oh sorry, that was the second, I'm sorry, I meant to do second row, first column, I get 0. Second row, second column, I get 1. Second row, third column, I get 0. Do you see where this is going? Here I get a half, a minus a half, and 0, so that becomes 0. Here I get zeros, and then on the last one, I get a half, and 0, so that sums up to 1. Boom. U times U transpose, or we could switch it around, U transpose times U is the identity matrix. That means U transpose is equals U inverse. So that's amazing. That's so easy to find the inverse. Let's just transpose it. Fantastic. We just wish all of our matrices were like this. They're the identity, of course, only if I'm sorry, it's the inverse if it's n by n. You can still get the identity if it's not. It doesn't have to be square matrices, right? This could be a 4 by 3 and a 3 by 4 or something. You can still get the identity matrix. But if it's a square matrix, then it's the inverse. So U transpose times U equals the identity matrix, or U transpose equals the identity matrix, and that implies just what I said. U is square, then U transpose is the inverse. And we call U, if they have orthonormal columns, we call it an orthogonal matrix. Now this is a little weird because orthogonal just means perpendicular. But when we say an orthogonal matrix, we actually mean the columns are perpendicular and the column vectors have length 1. So each is orthonormal, but they don't call it an orthonormal matrix. They just call it an orthogonal matrix. So that can be a little tricky. So pay attention to that. So we already talked about that. The U and U transpose is the inverse of U. So last two slides, just a couple properties. So, oops. If you have an orthogonal matrix, so the columns are orthonormal, and you multiply that by a vector, x, then the transformed vector has the same length as the vector you started with. So it does not change the length. If you have any two vectors x and y, then the dot product of x and y is the same as the dot product of the transformed x and the transformed y. And it's 0 if and only if x dot y is 0. So if x dot y is 0, they're perpendicular, they're orthogonal, and ux times uy, like these transformed vectors, they're also going to stay perpendicular. And we know that dot products are related to the angle, and so all of these come together to mean that when you do a transformation with an orthogonal matrix, that transformation preserves lengths and angles. Really, really, really nice. Here's a nice proof, algebraic proof here. You go along, you just rewrite the dot product as a transpose, apply your transpose property. Notice they reverse the order. And then you know that U transpose U is the identity matrix because U transpose is the same as U inverse. And you get down to you rewrite this as a dot product. So, okay, and I think this is the last slide. Yep. If U is an orthogonal matrix, then U transpose equals U inverse. We talked about that. Oh, and this is also orthogonal. So U transpose is orthogonal, and the inverse is orthogonal. The determinant of U is plus or minus 1. So this makes sense because if you're preserving lengths, then if you do a transformation and you preserve lengths, then you have to preserve area. If you don't change the lengths of things, if you don't change the lengths or the angles, then you can't change the area of any particular figure, and the determinant tells you the factor by which the area is changed. So it makes sense the determinant has to be plus or minus 1. The minus means it's changed orientation, like there was some reflection involved. The eigenvalues of U are always 1 or a negative 1. So in the directions of the eigenvectors, there's no stretching. So there might be some reversing the order. You might go from pointing in one direction to pointing the other direction, but there's no stretching or shrinking involved. U has orthonormal rows. So if the columns are orthonormal, the rows are also orthonormal, and the columns are orthonormal. So some properties for you to work with. All right, thank you very much.